Okay, let's continue where we left off last time. And if I can get the paper to sit still, maybe we will. Where we are about to go on to kind of a different way of looking at vectors. And sort of setting that up is one of the reasons why we might want a different method of looking at vectors other than the purely geometric approach that we've been using. So, what if you needed the resultant of multiple vectors, not just 2 or 3, but say 10 or 20 vectors? Doing it by the geometric methods, that would get really complicated really fast when you start analyzing more and more vectors at the same time. But if the magnitudes and directions of the vectors are known, then you can use what we call analytical methods to do it. For that, you need the x and y components of the vectors. You can find that if the magnitude and direction of the vectors are known. Okay. So we're using analytical methods. And you can also find the direction. What we're concerned about here is what's known as the direction angle, which we'll call theta A, if the vector is called A. And there are a couple equations that we can use for this. We've seen that you can draw the vector components for a vector. Say, okay, here's vector A, and you can draw the x component of vector A along, basically its projection along the x-axis, like that. And we started out drawing the y component of the vector as its projection on the y-axis, coming from the same origin as the original vector. But as we mentioned, the really only the things that define a vector are its magnitude and direction. So you can actually move vectors around as long as you maintain the magnitude or size of the vector and keep it pointing in the same direction. So it's perfectly permissible for us to move the y component of the vector over here and draw it like this. And now you have a right triangle. And the geometric rules for right triangles apply. We saw before that using the Pythagorean theorem, you can find the magnitude of the vector, and you can still do that. Now we have also a way of finding the angle. And the angle is the angle that the vector A makes with the x-axis. So that would be theta A. And the equations are fairly simple. Cosine of theta A should be the magnitude of the x component of the vector over the magnitude of the vector itself. And the sine of theta A is defined as the magnitude of the y component of the vector over the magnitude of the vector itself. This is all very nice to know, but what we're really looking for here is finding the x and y components. So you can rearrange these equations to find ax, which is just the magnitude of the vector itself, times the cosine of theta A, the angle of the vector, and ay is equal to a times the sine of theta A, or the angle that the vector makes with the y-axis. And these are the more important equations here, the more useful equations. But remember, these are really just rearrangements of these equations. So that's where that came from. That theta A again is the angle that the vector makes with the x-axis measured counterclockwise from the positive x-axis to the vector. Because the clockwise measurement would give us a negative angle. And actually, in most cases, you could do it that way and use the negative value for the angle, and you would come up with the same answer anyway. But we tend to go with the conventional counterclockwise from the positive x-axis. Okay. In doing this, we've got an example here, example 2.5, where they're searching for a missing child. And they're using bloodhounds to track the child. And basically, as bloodhounds often do, they'll get a scent, they'll follow it for a little while, then they'll go off in a different direction and pick up the scent somewhere else maybe. And so this bloodhound is kind of wandering around on several different trajectories during the course of finding the child. And what we're going to do is look at the vectors of those different trajectories and figure them out. So the bloodhound wanders and sniffs and does other stuff. And he's basically doing this in 5 segments. In the book, it refers to it as 5 legs, but because it's a dog we're talking about, it gets kind of, there's potential for confusing when you talk about the first leg, second leg, third leg, fourth leg, and then 5th leg. Wait a minute, where'd the dog grow a 5th leg? So I'm going to call them segments instead. Segment 1, and I'm going to put this information more explicitly than the word problem does, just for brevity. The dog walks 200 meters southeast, and then segment 2, (300 meters north). Segment 3 would be 50 meters 30 degrees west of north. 4, where are we here? 80 meters south, and 5, 150 meters 23 degrees west of south. Okay, so those are the 5 segments of the movement. And the question is, let's see, find the scalar components of the displacement vector and the displacement vector in terms of the components for each segment. Oh, and displacement. All right. Okay, so before we can actually go into this, we have to set out our directions here. As traditional, we're looking at east as being the positive x-axis and north as being the positive y-axis. And that leaves west to be negative x and south to be negative y. And we've got our unit vectors I and j, I being the unit vector in the positive x direction, and j being the unit vector in the y direction. Okay, so that's what we're dealing with here. For the segments, and we're working on the solution here, for the segments, segment 1 has a magnitude of 200 meters, and the direction is southeast. Southeast is the direction that's halfway between south and east. Going around the axes from the positive axis counterclockwise, the south direction would be 270 degrees, and going all the way back around to east would be 360 degrees. Halfway between those would be southeast, and that turns out to 315 degrees. Okay. Or 270 plus 45 degrees, because you've gone 270 degrees and then there's another 90 degrees to go all the way back to east, but you're only going half that far. So it's 270 plus 45, that's 315. You could, if you wanted to, go the other way, go clockwise, because it's closer. Clockwise from the east or positive x direction would give you an angle of negative 45 degrees for southeast. And you could use that also because the cosine and sine functions are the same for 315 as they are for negative 45. So you can do it either way. Okay, so the x component of the first leg, I'm going to keep L because that's what the book uses, because they're calling these segments legs. L1 in the x direction would be L1 times cosine of theta 1. That is the angle for this particular vector. And that's going to be 200 meters times cosine of 315, which is 0.707 something. If you multiply that out, you get 141.4 meters. So that's the x, the x component of the vector for the first segment of the dog's journey. Then we have the y component, and that's going to be L1 times sine of theta for the first leg of the journey. And that's 200 meters times the sine of 315 degrees, or negative 45. And that's negative 0.707. This was positive 0.707. This is negative 0.707. So you actually get the same number, only it's negative this time. Negative 141.4 meters. So the vector L1 for the first leg or segment of the journey is just going to be the x component of the first leg of the journey times the unit vector in the x direction plus the y component for that leg of the journey times the unit vector in the y direction, or it's going to be 141.4 times I, the unit vector I, minus 141.4 times the unit vector j meters. So that's the vector in terms of its components for the first leg of the journey, or the first segment. The second segment, same idea, only with different numbers. You first have to find the magnitude for the second leg of the journey, and that's 300 meters. And the direction is north, which according to our axes would be 90 degrees from 0, which is the east direction or the positive x-axis. So that's pretty easy. Yeah, x component for L2 is the magnitude of L2 times cosine of the angle for the second journey, or second leg of the journey. And that's going to be 300 meters times cosine of 90, and that equals 0. Because the cosine of 90 is 0. And the y component for the second leg of the journey is going to be, again, magnitude of L2, the second leg, times the sine of theta 2, the angle at which he's taking off during this segment of the journey. And again, that's going to be 300 meters. This time it's times the sine of, 90. And sine of 90 is 1. So this is 300 meters. So the vector L2 is just going to be the x component for L2 times the unit vector for x plus the y component for L2 times the vector unit vector for y. And that's going to be, basically it's going to be 0 I plus 300 times j meters. And because, of course, 0 times I is 0, you can leave that out. And this just becomes 300 meters times the unit vector in the y direction, or j. Okay, so that's for the second leg of the journey. For the third, the magnitude is 50 meters and direction is 30 degrees west of north. If you look at the directions, 30 degrees west of north would be right about here. Or in other words, it's 90 degrees because it's 90 degrees to get from east to north, plus another 30, which would be 120, I believe. Yes. Okay, so it's 120 degrees for the angle. And where are we? The x component for L3 is going to be L3 times cosine of the angle for segment 3. And that's 50 meters times cosine of 120. Cosine of 120 is negative 0.5. So when you multiply that by 50, you get negative 25 meters. And we need the y component for this leg of the journey also. That's L3 times sine theta 3. And that's 50 meters times sine of 120. And that's 50 times 0.866. And that's 43.3 meters. So the vector for L3 will be, or the third leg or the third segment of the journey, is going to be the x component for L3, or the third segment, times the unit vector in the x direction, times L3, the y component, times the unit vector in the y direction. And that's going to be negative 25 times I plus 43.3 times j meters. Okay, I think I'm going to pause the video here because the example is going to take a long time. You can try segments 4 and 5 on your own, and then when I unpause the video, then you can unpause the video, and we'll come back and compare notes. Meanwhile, I'm going to write that out, so it's not going to take as much time, hopefully. So I'll see you in just a moment. Okay, we're back, and I've done all that work, and hopefully you have too, and now we can compare results. I think we did L3, actually, which comes out to be negative 25I plus 43.3J meters. L4, the X component, you find, again, the same way we have before, and that comes out to 0 meters. For the Y component of the fourth segment, again, we do it the same way we did before, and that should come out to be negative 80 meters. And then the vector for L4 would therefore be just negative 80 meters times J. For L5, again, we do it the same way we did before. The direction is given as 23 degrees west of south, which means it's 23 degrees short of 270, because south is 270 degrees from the positive y-axis. So 270 minus 223 is 247. When you put that into the equations, you get the x component being negative 58.7 and the y component being negative 138.2. And so the vector L5 would be negative 58.7I minus or plus a negative 138.2J meters. If, and this wasn't part of the overall of the original question, but if you wanted to find the vector for the overall displacement from the original starting point at the end of segment 5, all you'd have to do would be add up the x components of all 5 of those segments and add up the y components for all 5 of those segments, and those would be the x and y components of your final vector. So I'm calling this LT for L total, or you could call it LF for L final, I guess. That would probably make more sense. But anyway, the x component for the total or final vector or final displacement would be just all of the x components added up. And that comes to 58 meters. The same for the y. Add up all the y components to get the y component for the overall final displacement vector. And that comes to negative 16.3 meters. And so your overall displacement vector for all 5 of those steps combined would be just 58I minus 16.3J meters. And if you wanted the angle of displacement relative to the initial starting point, well, again, you can go back to inverse tangent of the y component over the x component. And so that's just going to be the inverse tangent of negative 16.3 over 58, and you get negative 15.7 degrees. So you end up going something like about like that. That would be the overall displacement from where you started. And if you wanted the magnitude, again, you could use the Pythagorean theorem, where you would have what are we going to call it? We'll just call it LT. Square root of the x component plus squared plus the y component squared. So that would be the square root of 58 squared plus negative 16.3 squared. And so let's see, 58 squared plus 16.3 squared equals, we want the square root of that, raise it to the 0.5 power, and the magnitude ends up being 60.2 meters. So the length of this vector here would be 60.2 meters heading in this direction. Okay, so that's a pretty good overview of what we've known about vectors so far. And this also brings me to 25 minutes, so I guess I'll start up the next topic in the next segment.